217. In fact, I did 300. Okay, so you're already sitting on the YouTube. You don't have enough. Let's start. So, good morning, everybody. Please mute yourselves. Last time we said, so you're already sitting on the YouTube. You don't have enough. Fantastic. So we started talking about Hess's law last week, and we worked an example. If I remember the questions were related to how to know what to reverse. Why do we multiply? Why do we change sign? It all has to do with the fact that enthalpy is a state function. A state function depends on the state of the system and does not depend on how the state was achieved. So to buttress what we learned last time, let me work another example. So we're given this equation, NO2 going to NO plus half O2. This is also a thermochemical equation. We are given the states of the substance, and we are also given the heat of reaction. This is an endothermic reaction because you are supplying energy or heat to the system before the reaction proceeds. This is reaction 1, reaction 2. That one is exothermic. Reaction 3. This is what we are given. It is endothermic. The question is, find the enthalpy for the conversion of N2O4 to 2NO2. This is a rearrangement reaction. It's something that happens. So the question is, what is the delta H for this process? As always, what is important when you're using the concept of Hess's law? You look at the reaction that you're interested in, and then you compare it to what you're given. What you're given, you arrange it. Mute yourselves. I can't keep going back and forth. Arrange given reactions to align with desired reaction. So that is what we always do. So how do we go about that? This is N2O4. There's no N2O4 here. There's N2O4 here. It's on the product side. It means definitely we are going to reverse reaction 3. There's NO2 here. It's on the product side in the final reaction. If you look at reaction 1, it's on the reactant side. That means we are also going to reverse reaction 1. Also, there are 2 moles of it here. It means that we are going to multiply reaction 1 by 2 when we reverse it. So let's look at the solution. So we have that, so this is point, not comma. NO2 so from reaction, this is from the first reaction, so we now label it reaction 4. We are reversing the first reaction, reversing equation 1. Please mute yourselves. Odubanjo Shemilore. Again, so if we look at reaction 2, the reaction 2 is none of the entities in reaction 2 is in the final reaction. So why is it needed? If you look at it carefully, you would note that there are some things in both the equation 1 and equation 2 that we need to discard of. So the equation, there are some things in equation 1 and equation 3 which contains the species that we are interested in. So N2O4 is here, N2O4 is here. NO2 is here, NO2 is here. But there are things in equation 3 and equation 1 that we need to discard of, and that's why equation 2 was given. That helps us to get rid of those ones. So let's look at them critically now. Equation 1 has been reversed. It is now our equation 4. Equation 3 is also reversed. That's because equation 3 is reversed because N2O4 needs to be on the reactant side. It is on the product side in equation 3, but in the final equation, it's on the reactant side. So we reverse the equation 3. That becomes our equation 6. This becomes equation 4. So if you reverse equation 1, you have NO and NO2 here. If you reverse equation 3, you now have your N2O4 here. So the other entities that need to be rid of that are in equation 2 must now align with the new equation 4 and 6. So because of that, equation 2 was also reversed. Equation 2. So that it aligns with what we want to do. Okay, so next thing, after we have reversed equation 1, NO2 has 2 moles here, but here it has 1 mole. So to make it completely aligned, we need to multiply this new equation 4 by 2. So if we multiply equation 4 or reaction 4, let me call it equation, by 2, we get 2NO plus O2, 2NO2, and then we multiply this by 2 as well, because it is a state function. So once we multiply this, if you now add the new equations now, 1, 2, 3, if you sum all these equations together, let's see, do we have our desired equation? So NO, 2NO plus O2, this is equation 5, which is obtained from equation 1. This is this is equation 7, obtained from 1. Equation 5, obtained from 2. This is equation 6. So let's add them together. If you add all this together, so if you add all this together, let me write it out here. You would have 2NO plus O2 plus N2. I have not included their state just for clarity purposes, plus N2O4 plus 43 going to 2NO2 plus 2 times 13.5 plus 2NO plus N2 plus 2O2 plus 2 kcal. This is 43. Let me mind the way I write. So 2NO cancels out. N2O4, that's fine there. There's O2 here, that's 1 plus 1, that's 2O2. So it cancels out here. N2 cancels out. So we are left with N2O4 plus 43 going to 2NO2 plus 2 times 13.5 is 27 plus 2 kcal. So this is 29 in total kcal. So 43 minus 29 gives us 14. So that means the enthalpy, since it's on the reactant side, it means it's an endothermic reaction. And delta H is 14. For those that like to draw everything out, so N2O4 goes to N2 plus O2. That's the first equation that we're given. Oh, I promised to give you the slides today. You'll get the slides today. So these are the equations given. We're given these 3 equations, 13.02. So N2O4 goes to N2 plus 2O2. That's the reverse of equation 3. Because it's the reverse of equation 3, if we're going in this direction, it is 2 kcal. The reverse is minus 2 kcal. So equation 3 is N2O2 going to this. equation 1, 2NO2 plus 13.5 going to NO2 goes to NO plus O2. That's 13.5. But the 2, we have 1 here. So this will be 2 into 13.5. The reverse will be minus 2 into 13.5. So if you, for those that are, I'm solving the same thing. For those of you that are interested in looking at it in from a diagram, that in, sorry, for those of you that like to draw things out, that's another way to look at it. So we are interested in finding the delta X of this reaction. It's a matter of just summing up all things. The reaction goes from here to here and back to there, rather than just straight ahead. So that would be simply minus 2 plus 43 minus 2 into 13.5. And that will give you 14, like it gave us before. Was it 14? Yes. Anyway, so let's quickly take a look at, so we're looking at, we started with what enthalpy is, and it is difficult, the absolute value is difficult to measure. However, we can measure it, we can determine it from calorimetry. Calorimetry study of heat transfer, which can be studied at constant pressure or at constant volume. At constant pressure gives you delta H. At constant volume gives you delta E, which at times is approximated to delta H because the differences are small. But in accurate work, it is delta U. This is delta H, delta U, which is equal to its capacity times mass times change in temperature. Okay, so once where that's for processes, now let's look at enthalpy of reactions. For us to determine enthalpy of reactions, we need to look at enthalpy of formation of substances. Why? Because when you want to calculate the delta H of reactions, it is related to the delta H of formation of all substances. So enthalpy of formation of a substance is the standard enthalpy for the reaction for the formation of 1 mole of that substance. So standard enthalpy, formation of 1 mole of that substance from its elements in their reference states. All compounds have components. H2O, the components are H2 and O2 if I want to get a balanced reaction. So H2O2 is from H2 and O2. So the formation of H2O, the equation for the formation of H2O, so if we are looking at the liquid state or the gaseous state, is the reaction for its formation from its elements. The element present in H2O will be H2. O does not exist as O in its reference state. It exists as O2. So we put half to make the equation balanced. The reference state will be gas for both of them. So what is reference state? The reference state is of an element is its most stable form at a specified temperature, usually room temperature. Economics of things does not let us to start going up and down the temperature ladder, and at 1 bar, which is roughly the atmospheric temperature, atmospheric pressure too. So when you are saying something in their reference state, you're looking at the most stable state that we can easily get. Okay, so for example, the reference state of hydrogen gas is H2. The reference state of mercury, that's that liquid metal, is liquid. The reference state of okay, examples in the carbon is graphite. If you think about the reference state of phosphorus is pink phosphorus. Those ones that exist in different allotropes, you look at their reference state as the most stable form at ordinary conditions, usually 25 degrees and 1 bar. So the standard enthalpy of formation for ethanol that is given here, ethanol contains carbon, hydrogen. So you look at what it contains: carbon, hydrogen, and oxygen. How many carbon? 2 of them. How many hydrogen? 3 of them. How many oxygen atoms? 1 of them. So the reference state for its formation, the equation for the reference state of its formation will be, so I'm going to write it out. That will be on the product side. So carbon, the reference state of carbon is graphite. It exists as, it is monoatomic. Graphite plus the 6, oh sorry, not 3. There are 6 atoms of hydrogen there. Hydrogen exists as H2 in its reference state gas. So H2, if you multiply by 3, you get 6. And oxygen exists as O2 gas in its reference state. We have 1. To make it 1, we multiply by 1. So the equation of formation for liquid, this is ethanol, let's call it liquid. That is the equation of formation for the liquid ethanol. So delta H for this reaction will be delta H of formation for C2H4. Now, the standard enthalpy of formation of any element, not any substance, so any element in their reference states, the standard enthalpy of formation for the most stable form of any element, that means for the formation of that element in its reference state, is 0, because that is the standard state. That is the reference point in which it is. Meaning this is H2 gas. This is the standard state. So the standard state of formation will be from H2 gas. There's no enthalpy change. So any enthalpy change for formation of is equal to 0. So some other examples are given on the last line. Why is enthalpy of formation important? Like I said, it is related to the enthalpy of a reaction. That's the enthalpy change when a reactant goes to product. That is when you form new substances. This on this side here, there are standard enthalpies of formation of several things. If you look at this iodine solid, the enthalpy of formation is 0. That's because that is the reference states. But if you now look at iodine in the gaseous form, the standard enthalpy of formation is no longer 0. That's because you're looking at the formation from its solid state. Standard enthalpy of formation of liquid water and gaseous water, they are different. So you get the reason why it's important to always state the space in which you are working with. I'm moving too slowly. Okay, so delta H of formation of substances is important in obtaining delta H of formation of a reaction. So if you have a reaction and if you want to know the delta H of the reaction, so you look at the products, look for their delta H of formation, sum it up together, subtract the value, subtract from the value that you get the delta H of formation of the reactant. So for the reaction A plus B going to C plus D, the delta H of formation of that reaction is the delta H of reaction for this process. I think I have space down here, will be delta H of formation of D plus delta H of formation of C minus the sum of delta H of formation of A plus delta H of formation of B, products minus reactants. As an example, a quick example, so we're given this reaction. We have to calculate the delta H of this reaction. Given that delta H of formation of NH3, delta H of formation of HCl, and delta H of formation of NHCl. So if you look carefully at these reactions, these three reactions, you would see that they are enthalpies of formation because we are coming from the reference point of all of them. So 1 times 1/2/2 is the same thing as 3 halves. So this is a very straightforward one. So you have delta H of reaction will be delta H of the products. So we have only one product here, solid, minus delta H of formation of the reactant. So this is in gas and gas. Substitute the given values, minus 3.14 minus sum of that, and you get minus 176. Questions, confusions? Okay. There's nothing like I don't understand anything. Okay. Another example on the concept of
Ma,
yes.
please can you go back to the last slide?
This one?
Yes, ma.
Yes, ma.
Talking now. By now you should know I don't like it when you are not moved them talking
Why
quickly.
do you subtract all the products?
Subtract all the products. What does that mean?
Like enthalpy change of ammonium chloride minus enthalpy change of ammonia minus enthalpy change of hydrogen
That's
chloride.
simple algebra. If I put a bracket here, that would be plus. If I open the bracket, it becomes minus.
Okay, got it now. Thank you, ma.
Ma.
Oh yeah, hurry up.
Ma,
One
that kilojoules per mole. Please, ma, I just want to know how you derived or you got minus 46.1 minus 92.3 and that.
in the previous slide, there was a slide that I showed standard enthalpies, isn't it?
Yes, ma.
You see standard enthalpies of some compounds. So you have a table. In the last class, I told you that a lot has gone into generating data. So
Yes, ma.
you will be surprised that in the past 50 years, people have generated so much data. And that's one other reason why I'm sure all of you have heard about it. Data science is a lot of things.
Yes, ma.
There are so many data that has been generated, like it's of all this and all that. So you understand? So I'm not expected.
Yes, ma, I understand, ma.
I don't expect anybody to memorize all these values. You would be surprised that if you go to a library, you see a big book that contains standard enthalpies of formation. I don't expect you to memorize it.
Okay, ma, so that enthalpy that we did, ma, go to the next step, ma, please.
This slide?
Yes, ma. So all these minus 46, they are constants, like
They are
ammonium,
standard
this thing is
enthalpies.
constant.
So even if they are not constant, where I said it, given that. So
Okay,
this
ma.
is the case of Oyinbolonda Ilamu. Given that,
Yes.
calculate this, given that.
Oh, yes, ma.
So another example, if I'm to entertain all of you, I'm not going to do anything today. Still on delta H of reaction being equal to delta H of formation of products minus sum of that minus sum of delta H of formation of reactants. So use the standard enthalpies of formation to calculate the delta H for the reaction of carbon monoxide, the combustion of carbon monoxide to give carbon dioxide. So for the person that was confused the other time, so delta H of formation of the product minus sum of delta H of formation of the reactant. If I take out this bracket, the plus positive sign becomes negative. That's what I did in the last slide. So now let's look at this critically. So you notice that I have multiplied this by 2 because we have 2 moles here. In the standard enthalpies that we saw the other time, standard enthalpies of formation are always recorded in kilojoules per mole. It is 1 mole. It is not written per 2 moles. It is written per 1 mole. And delta H is an extensive property, meaning that it depends on the amount or number of moles of substances present. So this is 2 moles of carbon monoxide. So we are going to multiply the delta H of formation by 2. Similarly, 2 moles, 2 moles. Similarly, for the reactant, there's 2 moles of carbon monoxide because we multiply the delta H of formation by 2 moles because there are 2 moles here. And the delta H of formation of oxygen, we multiply it by half because we have half as the stoichiometry. Okay. From these values, I didn't write it out here. The values are given from that table that we just went to. Oh, there's a mistake there. So this O is supposed to be here, please. It's not supposed to be the denominator. It's supposed to be in the numerator. So from the table of values, the delta H of formation of carbon dioxide is 395 negative. Delta H of formation of carbon monoxide is minus 110. Oxygen is in its reference state. So the delta H of formation will be 0. So this is why this is not, sorry, this is not. So the half, this is the half, 1/2, and 0 is up there. If we press all this in our calculator, we arrive at that. So that should make those other questions clearer now.
Ma,
So, yes.
Yes,
how
ma'am.
is O20?
Please,
It is a
can somebody
constant.
from the class, other than whether it's a
It's
constant,
because it's in its reference state.
it's in its reference state. And what does that mean, that it's in its reference state?
It is the most
Equals to
stable
0.
form.
Sorry, I didn't hear that.
But because it's in its pure
Most
state.
stable form.
That is at the stable state.
It's
In
in
its
its
most
most
stable form.
stable state. Now, somebody said it's in
That's the
its
stable
pure
state.
state. No, that is not a correct answer.
It's
It's
at
in
the
its
stable
most stable
Okay, it is most stable
form.
state.
most
Most
stable
stable
state.
form.
In its
Okay,
most
so
stable
thank you for your answers. Let me
It is
throw more light
between
on it. Let me throw more
it
light
is
on it,
between
please.
10 bar and 25 degrees Celsius. Ma,
Let me throw more light on it, please. Thank you for your answers.
I said
Okay.
it is between
Oh, mo ti gbọ́.
It's okay now.
Let me throw more light on it.
it's
So,
between 1 bar and 25 degrees Celsius. Thank you, ma.
finally, thank you. So it's in its so the question is, why is that of oxygen 0? Number one, that person was not listening or his network was bad. So the reason is that oxygen and all other substances, oxygen in this equation is in its reference state. And when we say reference state, it means it is the most stable state. Most stable state. So usually, at times you may be told to calculate at a different temperature. So that will be specified. So, but most of the times we are talking about the standard state, the standard reference state. Standard state is about 25 degrees Celsius and 1 bar. So at that point, substances in their reference state, their most stable state or most stable form, the standard enthalpy of formation is 0. Now, the one that I was particular about is somebody said it's in its pure state. Now, the definition of a pure substance is different from the definition of a standard or a reference state or a most stable state. A pure substance contains only that substance. So you can have pure water, not the sachet water that we are talking about. So you can have pure water, liquid water. You can have pure steam. This is not a reference state. It is their standard state at a certain temperature, but this is not their reference state. Standard state is different from reference states. Reference is the most stable form at 25 degrees and
1 bar.
1 bar. Thank you. Okay, let's move quickly. You can have energy. So that's really all about thermodynamics that we want to talk about. The other thing you can calculate from bond enthalpies too. I think I'll share that note with you. So what's your question, please? All okay. All of you that have your hands raised up, please, can you put your questions in the chat box quickly? Let me go through them. Put your questions
How
in the
you know
chat box.
a substance?
Is 1 bar the same as 1 atmosphere? They are close, but they are not exactly the same. I've forgotten the conversion now, but they are very close. That's the one question. So you are looking at reference state. Somebody said something about reference state. I'm guessing it is the person wants to know. No, so you don't talk about reference state of water. Which equation is not balanced? Please balance it and solve it. Okay, I like Yamal. You came late. What is the meaning of 1 bar? That one is secondary school. So it's not about you coming, unless you came late to secondary school too. 1 bar, a bar is a temperature, is a measurement of temperature. So
Pressure.
reference states, measurement of pressure, thank you. Reference states, is that person a programmer? It's programmer no, it is not SI unit. It's programmers that are always looking out for other people's error. So reference states of an element. So we are looking at reference states of elements. It's different from standard state. Compounds in standard state, elements in reference states. So elements, the most stable form that you have. Are we supposed to memorize the values of form? Please, somebody asked, are we supposed to memorize values of formation? Well, if you can memorize 1 million, that's fine by me. Why didn't we use the same method you subtracted delta H? Because meaning there are several ways you can solve a problem as long as it is legal. Okay. So moving quickly now to just some basic concepts. You get energy source from food. Energy in food, that's energy released when the food is consumed. The energy value of food is often measured in calorimeters and is measured in kilojoules and calories. The energy in food is obtained from the nutrients that are present. Carbohydrates gives you 4 kilocal per gram. Same thing with proteins. Fats gives you the highest energy, and they give you long-lasting energy too. Alcohol does not give, that gives you energy but no value, and then you have fiber giving nothing. So if you look at some of the energy sources of our daily food, we have them. So I'm going to share this slide with you. You can play with it. Some people keep asking the same question over and over again. See, this is some energy sources in our beautiful Nigerian diet that a lot of us are not willing to give up the activities. You can also get energy from fuel, day-to-day energy. Fuels store, and this one I'm interested in. Fuels store energy in their bones, and they release that energy when they undergo chemical reaction. The chemical reaction that they undergo mostly is combustion. So these are different sources of fuel that we have that are primarily used now, depending on where you want to go. So that brings us to the end of thermochemistry. And then, any question? We now talk about, we're going to start talking about some other concepts now. Another thermodynamic concept. Ugal,
I have a question.
please go ahead. Hurry up,
Yeah.
we don't have time.
Concerning the units, sometimes we use liters and some unconventional units. Is it always proper to use those units that are not metric units?
Okay, so for example, let me give you something. If you go to America and they are talking about the temperature, they are going to talk about the temperature in Fahrenheit. If you come to Nigeria, we'll talk about the temperature in Celsius. Some part of Russia use one old temperature unit. Now, that aside, when meteorologists are talking about pressure, some talk about it in millimeters of mercury, some talk about it in bar. Long and short of what I'm trying to say, and we're telling you a little bit of story. Somebody was trying to tell us a story of how the daughter survived a temperature of 120 degrees centigrade. Now, if you hear that, if you're in Nigeria, you will be like, that doesn't make any sense, right? But
Yeah.
the person was referring to Fahrenheit. In Celsius, the normal body temperature is what? About 36. If you convert that to Fahrenheit, that gives you about 98 Fahrenheit. So that's 98 Fahrenheit. So what I'm trying to say in essence is, when you are working with units, when you are doing any form of calculation, it is imperative and very important that you state your units and state your conditions. And that is why I've emphasized it in the previous classes, that anytime you're doing anything, you state the condition in which you are working on. If you don't state the condition, the person reading it will misunderstand. And if that person misunderstands and builds on that experiment, that's already a failed experiment from the start. Now, the advice that I give is to always convert to the SI unit. Even the person that is in the norm that they work in Fahrenheit, when they want to report in the standard form, in the conventional form, they will convert to Kelvin. We don't use Kelvin. The normal body temperature in Kelvin is not 35. If we're going to talk about Kelvin, that would be 35 plus 273. Did that answer your question?
Yes, ma'am. But I still want to know if it's advisable to walk through with a given unit and then towards the end.
I answered that question when I was talking, that you should always convert. Abi? That means you're
Yes,
not
ma'am.
listening. And you still want to know something else again. Okay.
Ma,
Yes.
So like I wanted to ask about
But you don't want to
the
answer again.
reference state.
No, I've answered reference states. Please watch the video again. I've answered reference states. Okay. So the other topic that we are going through is spontaneity. That is reactions occurring without aid. So a quick review, we have already said that energy cannot be destroyed. The total energy of the universe is constant. Energy can be converted from one form to another. In the field of kinetics, we study how fast a reaction can occur. In the fields of chemical equilibrium, I don't know if you've talked about it, but I'm sure you will talk about it. That tells you how far a reaction can go before it reaches a stable state. Please, I'm the only one that is supposed to be talking. Eromosele.
I'm not done. I was talking.
I'm seeing it here. Somebody is talking behind you then. So mute your mic before you go into an argument with me. Better, good boy. So equilibrium talks about, so in the field of chemical kinetics, how fast a reaction will occur, whether it's going to be flow or equilibrium talks about how the extent it reaches, in the sense that, okay, once the reaction starts, when does it reach a stable way that the rate of the forward and the rate of the reverse are the same? That's equilibrium. Equilibrium is balance. However, does a reaction occur without somebody needing it? There's somebody prompting it or any external force to happen. Thermodynamics can also help with that. We have 10 more minutes. I'm not supposed to come on Friday, so what do we do? I think I will beg the lecturer for Friday. So a spontaneous process, like this one here, if you put a nail outside or a metal outside, what happens? It rusts after some time, as long as it's in contact with water. Well, not all metals, but most metals. I think all metals. It depends on how long it takes. A spontaneous process is one that occurs without the need of any external input of energy. That's the definition of a spontaneous process. And that's why we define spontaneity as a reaction proceeding without external input. If I carry, this guy is carrying 2 eggs here, whether it's consciously or unconsciously, it drops the 2 eggs. What happens? The 2 eggs will come to the ground, and if you have enough force, what happens? It breaks. If you put a gas inside a container, like any form of container, the moment you open the container, the gas will expand to fill any place. So all these directions, these are spontaneous processes. The reverse processes are not spontaneous. We call those ones non-spontaneous process. They will not happen unless, some of them are even impossible. The egg that broke now, I don't think it's possible for you to take it back. If it did not break, it's possible to take it back. So the reverse processes are usually not spontaneous and at times not possible. For the gas to go back here, you'd need to force it in that direction. But for it to go back on its own, that will not happen. So processes that are spontaneous in one direction are non-spontaneous in the other direction. We also need to note that a spontaneous process does not necessarily mean a fast process. It can be slow, it can be fast. This was a fast one. This is a very slow process. This one is also a fast one. Immediately you release the gas, immediately it starts going in that, it starts filling up. So That means that the processes also depends on the standard conditions or the conditions in which the process is taking place. For example, if you put ice inside this container contains ice. Once the temperature is above 0 degrees Celsius, it spontaneously converts to water. If you bring the temperature to minus 22 degrees Celsius, the spontaneous direction is that it forms ice. It forms solid H2O. Now, there was somebody that suggested that an exothermic reaction is spontaneous. But from what we just described here, this reverse one is endothermic. And considering the temperature, it was a spontaneous reaction. So delta H is not a condition to determine whether a reaction is spontaneous or not. Before we close for today, so that we start them on Friday, before we discuss the concept of entropy, that's the one that is related to spontaneous. I want to quickly talk about just this last slide. Reversible and irreversible processes. This concept, we need it because we looked at the ice going to water, and under a different condition, it can go back to ice. Anyway, so let's leave it at that. However, in the context of thermodynamics, a reversible process is one that changes in such a way that the system can be put back in their original state. Long and short, a reversible process is a slow process that you can easily go back to your initial state. An irreversible process cannot be undone exactly by going back to the way you're coming from. We will continue from here on Saturday. Good morning to everybody.
Thank you,
Do
ma.
you still have any question?
Ma, please, can you go back to the second to the last slide?
Saturday or Friday?
No, I'll send the thermodynamic slide. The first one, the first
Yes.
lecture, I'll send that slide today. This
Yes,
one?
ma'am. Thank
Yes, ma.
Ma, what of on Thursday or Friday? We have free time by then. One weekend.
What about me? Do I have free time? Oh, Benny, don't have question. Ask your question.
No, ma. I just wanted to see the slide.
You're not serious. You're not stressing me. So, what time do you have? What free time do you have on Thursday? Auntie?
I have a question. I'm not sure everybody's schedules are aligned, no.
Oh,
Sorry,
yeah,
ma, I have a
Milena.
question.
Madalo.
Go ahead and ask your question. 5, 4, 3,
I have a question.
2,
1.
Bye bye.
Thank you.
Okay.
That was
I noticed that